Okay, so what I am going to do next is to try and complete the discussion on PalmDPs and handle any other questions you have about the topics. I mean, everything until today would be fair game for midterm. I realize that PalmDP, we haven't had a homework, so clearly I'll take that into account. But you have come to the lectures and you have read the readings, so you should know at certain level, how things are. And there would be a separate homework-ish part on PalmDPs too. That will be coming up soon. Okay. Yes.
Are we allowed to bring computers?
What?
Are we allowed to bring computers?
For doing what?
For doing midterm
No. So for what would you plan to use the computers for?
evaluation, calculations?
No, you can get calculators. Yes.
Okay.
You can get calculators.
But what about like complex?
No, you are not using MATLAB. I would not be requiring you to use MATLAB as part of the homework, as part of the exam. Okay?
Calculators, like what type of calculators?
Any type of calculators.
Can a smartphone calculator?
What? What?
Can I bring a smartphone calculator?
No. Since you ask, I assume there is something about it, so I would say no. I don't know. No, I mean, honestly, I think it's not going to be. I mean, you probably would need a reasonable small calculator. That's about it. I mean, when I won't allow any smartphones that will allow MDP applets, to be thrown in, for example. Okay, so that doesn't make any sense. Okay. Other questions? Okay, so continuing along. So last class we were talking. So last class we basically understood, I hope, the execution model of the PalmDP. Okay, and mentioned, of course, that once I know the execution model, I can directly go actually to the. I can go directly to the a look ahead approach for solving PalmDPs. Okay, so basically, what you would do is you would basically know your initial belief state or your current belief state, and you have certain amount of time, and you essentially simulate the PalmDP. Okay, and then so in simulating the PalmDP, basically these are your actions. So under this belief state, so you have these are your actions. Okay, actually I should not put that kind of a thing because it's not meant to say that all actions should be done. One action should be done. So you have to decide which action to do. The thing, of course, is when you do the action during the execution, you will get some evidence after that action. Okay, and you don't quite know which evidence you will get. Okay, so then you have in execution model, you would do the action, get the evidence, and then compute the belief state. Right? Here, you consider for every action and for every evidence, you can compute the belief state. So that's basically was available in the execution model. Okay, and once you have that, then you basically come down all the way to whatever number of whatever depth you want. Let's say k depth, and then of course the question is okay. The question is okay. Yeah, the question is, what do you want to give as the values for those guys? Right? You need to give values for these guys. So actually, I want to point out that normally what you would like to do is, of course, you could say, now if you happen to know how to solve that belief state, if you can compute the value of that belief state correctly using the PalmDP model, that would be great. But if you knew that, you could have done that on the top also. Okay, so we assume that you don't quite know the value of these belief states. So you need to approximate it. Okay, now remember for MDPs, when you were doing this for MDPs, what would you have put here? You would put some heuristic value. You see what I'm saying? I mean, one heuristic, for example, was this all outcomes heuristic that was used in the LRTDP paper, for example. Okay, so here, so in our, when I say heuristic, that means I'm sort of relaxing the problem so that the problem is easier to solve, and then I'll get a bound. Okay, one interesting question is, for POM-DPs, what would be the way you would approximate, what would be the way you would relax in a systematic sense? Okay, one idea would be that I can say the POM-DP is right in between non-observable MDP and fully observable MDP, right? I can sort of relax it, technically relax the partial observability constraint, and it will become fully observable, right? And then that would be MDP, which is what we were sweating bullets about a couple of weeks back. That looks like happy friend to us now, because MDP is nothing, I mean, compared to the POM-DP, POM-DP value computation. Okay, so one thing I can do is, for each of these belief states, from each of these belief states, I will compute the value there using essentially an MDP approximation. You see what I'm saying? One idea would be that a belief state has, it's an expectation over states, and if I can compute the MDP value function, and then take the expected value of that, so basically the probability that you're in state 1 times the value of that state 1 plus probability that you're in state 2 times the value of the state 2. Except the values are coming from the fully observable MDPs. You see what I'm saying? If you do that, then the question is, it's going to be approximate. What kind of approximation is it? Is the true value going to be, the true value of this belief state going to be higher or lower or equal to this?
As compared to the MDP value?
I mean, the true value being the POM-DP valuation, right? The POM-DP, if you actually computed the POM-DP value function, then that would be sort of the H star here, okay? And you're getting an H right now, which is basically solving it using MDP. So then the true value would be what, upper or lower bound? But the value, the approximation would be an upper or lower bound on the true value. It would be an upper bound, right? Because after all, you are hoping, you are expecting that you have more sensory information than you actually have. If the sensory information increases, the value cannot reduce. You see what I'm saying? If the sensory information increases, the value cannot reduce. Okay, so if I take the POM-DP approximation, that's one way of doing it. I can do the POM-DP approximation, compute the values for these guys. Okay, and then take the expected value of this node, and then I can back it up. Now, how would I back it up? Basically, to back it up, I notice that under the, so if I have the values for these belief states, right, I can then, the value that I get here is going to be essentially expected value of this, because I can be getting in the actual, during actual execution, I might get this evidence E1 or this E2 or this E3 or this E4. I don't quite know which one I get. Okay, so I have to take probability of getting evidence E in this belief state, okay, times the value of the belief state, times the value I'm getting from that branch. That's the expected value. Okay, now on the other hand, here I take the max, because this is where I get my free will. Right, because I can do action A1 or A2 or A3 or A4, whichever will give me more value, that's the one I'll take. You see what I'm saying? It's like expectation at the evidence level and maximization at the action level. Expectation at the evidence level and maximization at the action level. Okay, and if you do that, then in essence, I mean, you essentially have the ability to write such a tree. and using that, you can compute the best action. And the more time you have, the deeper you can go, for example. Okay, now one other interesting thing, of course, is right now you dealing with only an upper bound approximation. But I could actually also deal with a lower bound approximation. Basically, it's POMDP. I can decide to say I just have no sensory information whatsoever. Just as I have full sensory information, I can say I have no sensory information. That will become NOM-DP. And we didn't talk about this specifically in this class, but essentially it's a special case of POMDP, which is not having any sensory information whatsoever. And remember that if you have no sensory information whatsoever, then in essence you will just do a sequence of actions. Right? Okay. So the idea, what I have in mind is that if you don't have, so one of the things I pointed out is for POMDPs, the usual plans that you'll be considering, in a minute we'll be talking about it, is let's say do action A1, and if you get E1, do A2, if you do get E2, do A3. This is how the POMDP tree policy, these are called tree policies, we'll talk about it in a minute. And this is how the tree policies would look. Okay, now if I don't have any evidence, if I'm not going to get any evidence, then clearly my plan would just be a line. Do action A1, then action A2, then action A3. You see what I'm saying? And in particular, now notice that here I talked in terms of actions, but really I could be talking in terms of belief states too. So I have one single belief state, initial belief state Bi. Okay, once I know the belief state, if I do an action A, I can compute the new belief state. There is a unique new belief state. Right, that's what we talked about. Even though actions are stochastic, after the action, the belief state is unique. Right, so I will get A of Bi. Then I'll, let's say, this is A1, so A1 of Bi. And I do A2, then I get A2 of Bi. So this is how I think about how the world will evolve. You see what I'm saying? So the tree policies would be line policies for NOM-DPs. Okay, and it actually turns out that there is another name for it. It's called conformant planning. In fact, I'm pretty sure in the 2 videos you watched when I wasn't there, I talked about conformant planning. Okay, so a conformant planning essentially says I have uncertainty in the initial state, but there is no way of resolving it other than by doing actions. And when the uncertainty gets resolved, I cannot sense that it got resolved. I just have to reason out that it must have gotten resolved. Do you see what I'm saying? Okay, so the classic example I'm pretty sure I've told you is I may not know what's on this table. So is the table clear or not? I have no clue. There may be things on it. So it may be clear, it may not be clear. Okay, so I cannot say, I cannot say I can sense and see whether it's clear or not, because that's the point of not having any sensing information. Okay, however, I can do a sweep action. So sweep from the top to the bottom. Okay, when I sweep, then everything falls off. And after that, I know for sure that the table is clear. So I reasoned out and removed the uncertainty in the state, not by sensing. Okay, and we discussed a lot in that conformant planning part, non-deterministic conformant planning, that there are situations where this can be done, there are situations where this cannot be done. I mean, in particular, if those of you remember the Medicaid example, you know that there is no conformant plan for Medicaid. It's not, you can't just, doctors hope so sometimes, right? That I'll give you both an antibiotic and an antiviral medication and an anti-somnolence medication and hope for the best. Okay, sometimes that doesn't work, because if you are not suffering from a disease, if you get the medicine for that disease, you might die. So you actually need to do tests. And I hope you remember all that discussion we had in that particular part about the fact that the tests actually cost. And so people sometimes want to come up with conformant plans even when there are conditional plans available with higher quality. Higher, but the point is the cost is higher for the tests sometimes. You see what I'm saying? In fact, insurance agencies, most of the time, they stop your doctor, medical insurance agencies, most of the time, they stop your doctor from doing tests. Because if you are a medical practitioner in this country, what you really want to do is to have done every possible test so that eventually when you sue the guy, they can say, we did check everything possible. And we did this, we made this happen, right? Because if they in good faith actually missed a particular thing, it's not that we're going to take them, oh yeah, it's like they did the best they could. No, we won't do that. We would actually, because you'll be watching late night TV and then Goldberg has gone, the injury lawyers will come and then we'll go with them. And then we'll say, you have to pay money because you did not see this particular really implausible disease that I might have been suffering with. You didn't check this. So if I'm the doctor, I would say, before I give you Tylenol, I would do 18 million tests to avoid my risk of being sued later. And if I'm an insurance company who is paying the doctor, I'm going to be dead. The reason, for example, any prescription medication costs, the treatment can cost a lot if in fact you do humongous amount of tests before giving the first medicine. So insurance companies will regularly say no, no, no for most of the tests. And the doctors will regularly say do more and more tests. And you can understand this completely in terms of conditional versus conformant plans. Insurance companies would like the doctors to do conformant plans. They're cheaper. Unless, of course, the conformant plan will lead them to do some really costly medication, then in which case they'll say, do the test first. Okay. So anyway, if you do the NOM-DP and then solve, you can also solve NOM-DP value function. We didn't talk about it here. There are techniques for that. And if you do that, you will get a lower bound on the value function or on the upper bound on the cost function. Okay, so one of the nice things is just from this, so this is what I'm saying here, whatever I just said till now, are you can either over constrain it to a NOM-DP or relax it to be a form-DP. Okay, by the way, any of you linguists here, do any of you know retronyms? A retronym. This poor guy used to be just called MDP before. Right? Now that you know POM-DP, we call him FOM-DP. Okay, that's what used to happen. We used to, you're too young, but they used to be just normal events. And then microwave ovens came, and so normal ovens became conventional ovens. Okay, and whatever phones we are calling, we used to have, now they call landline phones, and then there is cell phones. So you keep changing backward. Okay, that's called a retronym. So FOM-DP is really fully observable MDP. We did not have to make that distinction before when we had only one MDP. Now that we have POM-DP, then we need a FOM-DP. And you also need a NOM-DP. Okay. And then, okay, so those two will give you upper and lower bounds. And in fact, one of the nice things is you can, actually this is a paper by that I don't have the link here. Actually, I should. Do I have a link here? No. They basically work which shows that if you have both upper and lower bounds to these lower belief states, then you can do better than just having one bound. In particular, if one of your options has an upper bound value that is lower than the lower bound value of the other option, then there is no point in considering this option. Right? So what I'm saying is, if I do this action, I'll get between $10 and $20. Okay, 10 is the lowest, 20 is the highest, okay, that I can get. And if I do this action, I get between $30 and $40. Then why would I consider this? You see what I'm saying? So you could actually do interesting pruning if you consider both bounds. Okay, something that is accessible enough to you. Of course, this picture also shows you that if you only had one, this is what I had. This is a less busy picture than the previous one. Essentially, I'm computing, if you're only just using one bound, let's say you compute 14 as the FarmDP bound here, and 12 as the FarmDP bound here. And then this is, you get this with 0.6. This evidence will come with 0.6 probability. This evidence will come with 0.4 probability. So you can compute the average upper bound here, which is 0.6 times 14 plus 0.4 times 12, 11.5. Okay, and then this belief state guy then is getting 11.5 from here and a 16.9 from here, assuming you only have one bound. Okay, then would basically know that heuristically I would go with this. You see what I'm saying? Okay. Okay. Now I want to go back a little and also talk about, yes.
In that case, in 6 and 40 and 9 and 12, if I had to choose, which one would I choose?
Which one? What?
In 6 and 40, the leftmost.
No. I basically choose after having made, this is all simulation, remember?
Yeah.
Okay. So I would get backed up values. So in fact, in this particular case, if I'm only using one single bound, on this left-hand side, A1 is giving me a 17.9 bound, and A2 is giving me a bound that I seem to have.
So basically, I'm trying to know what happens in the case of intersection. Like you don't have.
No, that's usually to read the paper in that case. Basically, so because you have both upper and lower bounds, and if there is an intersection, then you have to basically probabilistically choose with the probability distribution provided by the upper and lower bound. Okay, that's more interesting, more sophisticated. Okay, I will send you guys a link to this paper. It's actually easy to read paper, and it might be probably like, because I'm going to about to start talking about the value iteration algorithm, mostly to say that you have heard about value iteration for POM-DPs, but it's a reasonably ugly algorithm. Okay, and if you really have to use POM-DPs, you're more likely to. I mean, you will have to use POM-DPs. They're great tools, and you're more likely to use this sort of things, more approximation ideas than exact ideas. But you should know how exact idea works. What?
The approximation algorithms of FFT value and everything can come.
Well, that's a good question. You can ask, you can tell me. FF replan in essence assumes, what does it assume? I mean, so it really is a question of FF replan was meant for fully observable scenarios. You could do it. So even if it's partially observable, you can use essentially, FF replan style, I mean, those kinds of approximations here too. Okay, I mean, in general, I think it's actually nice to know that one of the things that I want you to understand is, if you have a complex problem, okay, and you really would like to just, I mean, one of the biggest questions, and in 471, I ask students all the time, okay, so in min-max search, you go k-deep, and then you apply your silly evaluation function, which is like, the number of pawns plus the number of 2 times the number of knights plus 3 times the number of bishops divided by some random factor. That is the evaluation of this chessboard. If you believe that is really the value of the chessboard, why didn't you apply it in the top itself? Okay, there is a lot to be said for doing approximation deeper down the search tree. Why? Because essentially by actually just expanding the game, you can at least spot obvious traps. In fact, in min-max analysis, that's been shown. By expanding the game, you can at least spot the obvious traps.
You have better visibility.
Yes, it's not, I mean, I think it turns out it's a trickier point than that. In general, actually, so the idea, of course, is, yes, you have better visibility, but the point is, you're still only applying the approximate value here. So what did you get? What you got is the topology of the search space might make visible some traps that you wouldn't have seen at the top. So for example, you are at a obvious dead chessboard, in the sense in 2 moves you're dead. But you basically are just you're just counting the pieces and thinking, I'm still fine. if you actually just play, if you just expand the chessboard by just the normal rules of chess, you would find that in 2 moves there was this move, which will basically kill the game. So even you have to realize that. You see what I'm saying? So, and in general, when you are, faced with a, complex problem, try to avoid the temptation to approximate it upfront. Let the search of the problem take place for, let's say, k depth, and then do the approximation, and then you do better. And again, the intuition for this is coming from the max tree. Okay. Okay. Yeah.
Is the max operator independent of the lower and the upper bounds?
What? No. Okay. So I basically wanted to show you that you can have lower and upper bounds. I'm not teaching you this algorithm right now. I will give you the paper. You can, as far as I'm concerned, if you understand that, if I give you one bound, you can do max up. That is good enough. But I'm also telling you that, in fact, getting into that aspect is kind of iffy because I didn't even teach you how to do non-DP policies. I mean, it can be figured out, but I didn't teach you. Okay. So the last thing that I was mentioning at the end of last class basically was that we have really what you have in front of us is a belief MDP, even though we don't really use this as much. It's kind of funny. In fact, I want this slide basically shows that MDPs are really MDPs in belief space. But we don't really use this in any of the algorithms. Okay, in both the exact algorithm for finite horizon, as well as the algorithms that I just showed you, the approximation algorithms, you did, well, in approximation algorithms you did use the belief state, okay, but the exact algorithms you want. Okay, so here basically all this is showing is that you now, in the belief state MDP, the states are belief simplex. That means any point on the belief simplex is a state. Okay, and that actions are the same as before. The reward is basically expected reward of the states. So if you have a belief state, okay, B, and it's a probability, if you have 2 states and the belief state is 0.5, 0.5, then the reward for being in 0.5, 0.5 belief state is 0.5 of the reward 1 plus 0.5 of the reward 2. That's the expected reward. That's the only thing you can do. Okay. So you now computed. So you basically have defined a reward for the MDP. You have the actions. You have the state space. The only thing you need is the transition function, and I can directly write the transition function in terms of the belief states. Okay. And what this is saying basically is the probability that I'll get a belief state B dash when I do belief state B and do action A in belief state B is essentially given by that particular probability is given here, and that now depends, of course, on the fact that when you do A in B, you might get different evidences, and so you condition on the evidence. Okay, so you compute this as a summation over the different evidences, okay, that you can potentially get when you do action A in belief state B, B dash B A E, and the probability that you will get that evidence E when you do action A in belief state B. Okay, of that, this, as I mentioned, I hope you looked at this. I said that you should look at it. This essentially, this probability distribution would be a degenerate distribution. It will only be 1 for one particular belief state and 0 for everything else. And that belief state would be given by our update function. Because you know the evidence. If I know the action on the evidence, then I know exactly what the belief state would be. Do you see what I'm saying? It's like, it's sort of confusing because you'd expect, since it's a probability distribution, it should give values for every belief state, probability values. But yes, it does. It gives zeros to everybody except for the one belief state that will occur when you have this evidence. Right? Okay. Now the only question then is, what's the probability that you'll get evidence E given that you did action A in belief state B, and that you are now going to condition over the state that you actually are in, unbeknownst to you. Okay. Now the interesting thing, of course, is in PalmDP is basically there is no state superposition, right? In the sense, in the end, the real world knows the exact state it is in. Unlike quantum uncertainty, where apparently the real world also doesn't know where the state, what state it is in. Here, the real world knows which state it is. You don't know which state it is in because you have nowhere observed. Right? Okay. So the question, of course, is what is the probability that I'll get evidence E when I did action A in belief state B? That depends on which state I actually wound up in. Suppose I wound up in state S dash, then what's the probability that I'll get evidence E if I got to S dash having done action A in belief state B? Now notice that turns out to be PE given S dash. That's the Markov assumption. The observation depends only on the current state, not how you got to that current state. Right? And PE given S dash is known. That's part of the model. Right? And then the other part, of course, is how did I get into S dash? What's the probability that I would be in S dash if I did action A in belief state B? That I can compute. Because I know the new belief state after doing action A, after doing belief state B, and look at the probability that's assigned for S dash in that belief state. And that's what I'm going to do. And this was, by the way, this part was the first step of the execution model, where it does action A, it computes internally what it is expecting the belief state to be. Then it gets the evidence, it updates the belief state. This is the first step. Okay. Having done this, now I would say that I have given you a belief, an MDP for your quantity. And it is indeed Markov because, essentially the transition function depends only on B and the action A, nothing else. Okay. So that sort of technically shows that PalmDPs are indeed belief state, are MDPs in the continuous space of belief states. Okay, and then we of course have figured out how to find how to do execution of PalmDPs and also how to pick actions, approximately at least. Okay, so the last thing I want to do is to talk about how you go about computing the optimal value function for PalmDPs. Again, as I said, you should have read it a couple of times by now because I said 2 times to read that. It's only a couple of pages, but I just want to go into a bit more detail just to make sure that your intuitions get kind of more stronger. So the thing that of course, you have belief states. You have the specific thing we talk about is policy trees. Okay, so in essence, I'm basically thinking if I only have k steps to live. Okay, if I have k steps to live, my horizon is k, then I need a k depth policy tree. Okay, and the k policy tree, the depth policy tree would have to say, okay, currently do an action and see what evidence you get. Based on that, do this action, see what evidence you get. Based on that, do another action. You see what I'm saying? And one of these policy trees of depth k must be the optimal policy tree. Because this only makes sense because we are talking about finite horizon MDPs. You understand what I'm saying? Okay. So in essence, I'm basically computing a k depth policy tree that is optimal. Okay. And to do that, I do again the dynamic programming. I do one depth policy tree, and then using their values compute the 2 depth policy trees. Using their values, compute the best 3 depth policy trees and so on. Okay, and to compute the optimal k depth policy tree, you basically go bottom up. Okay, so the way it sort of looks like the other thing that to notice is that if I essentially these are of course these are 1 depth policy trees. right? If I only have two actions, A1 and A2, and I can only do one action, when I only have one job, then I do the action and that's it. I don't even have time to see what the evidence is. How does it matter? I do the action, I get like singeing sensation. I say, sorry, that's what I get. It's not that I'm going to have another chance to do a different action. Is what I'm saying. Okay, so if I do one-step policy tree, so one of the interesting questions is, if I know which state I was in, let's say, suppose I only have two states, S1 and S2. If I know which state I was originally in, and if I do an action, I know which state I would be in if it's deterministic action. And then I can read off the reward for that state. Okay. However, right now what happens is that you are talking in belief states. If you're in belief states. If you're in belief states, then depending on the specific state you actually wind up being in, you will get a different reward. And since you have different different belief states will give different probabilities. Let's say this is one belief state, this is another belief state, and so on. Okay, I can essentially then compute. So, for example, if I do action A1 in belief state S1, okay, let's say, then I get this as the value. If I do action A1 in belief state S2, I get this as the value. Then as I progress on this is from 0 to 1, so as I progress on this, I'm changing the relative proportion of probability between S1 and S2. This picture only makes sense for a two-dimensional case. There are two states. The simplex can be nicely shown as in this form. It becomes three states, it will become that triangle in three-dimensional. Case states, I can't even show you pictures. Okay, so we are trying to get sort of a geometric interpretation of n-dimensional hyperplanes, really. Okay, so the point we are making here is that the value, if you are in state S1, for action A1 would have been this. If you knew you were in state S2, the action A1 value would have been this. So clearly, the value as the probability changes between S1 and S2, the value sort of linearly changes. So if you do A1 all the time, depending on the belief state, each point here is a belief state. So the value of your action or your policy, single action policy, changes like this. Now similarly, I can do this for A2. Right? Okay. So the question then is that if I do A1 this, is A2 this, then however I get to choose. I am an agent with free will. So I thought this through, I get to choose which action to do. So then of course I will do the upper bound on these on these lines. So in particular, up to this part, I would do A2. Any belief state between here and here, I will do A2. And any belief state between here and here, I will do A1. You see what I'm saying? Let me then go to actually, let me make sure that we get this clear with the example that was in the textbook. Okay, so the textbook example was these two states, the states 0 and state 1. Okay, and they had reward for the 0th state is 0, reward for the first state is 1. And then they had two actions, stay and go. Stay would stay where you are with 0.9 probability, goes to the other state with 0.1. Go will go to the other state with 0.9 probability, stay in the same state with 0.1. Up until then, it's just an MDB. Then your life becomes hard because I throw this in. The sensor model. The sensor model tells you the correct state with only 0.6 probability. You see what I'm saying? So if you are in S1, you will get, say, observation O1 with 0.6 probability. And you can get observation O1 in S2 with 0.4 probability. And similarly, if you are in S2, you will get observation O2 with 0.6 probability, but you will get observation O2 in S1 also with 0.4 probability. You see what I'm saying? So if this is changed such that 0.6 becomes 1, then it is MDB. If it is changed such that the probability becomes 0, then it's non-MDB. If it's 0.6, 0.4, it's bounded. Any number in between 0 and 1 is bounded, right? So then we were considering, after that, we were considering the single action plan. So obviously, since there are only two actions, stay and go, and if I have one horizon, my horizon is 1, I'm trying to actually compute a k-horizon policy tree. But to do that, I would compute first the one horizon policy tree, and then piggyback on it to compute the two horizon trees, piggyback on that to compute the 3 all the way up to the kth horizon, and then pick the test at the kth horizon. See what I'm saying? Okay, so the interesting question is, so basically, I mean, in this case, so if the notation they use is alpha of p, a particular policy tree p, what is the value of doing that policy tree p in a particular state 0 in this case. If I know that if I'm doing stay in 0, the value I would get would be 0.1. Okay, and then similarly, if I do it in 1, again, I hope you understand why that is the case, right? Because even if I'm in 0, if I do stay, with 0.9 probability, I will stay in 0. With 0.1 probability, I will go to 1. So with 0.1 probability, I will get the reward of 1. With 0.9 probability, I will get the reward of 0. Okay, now I'm also throwing in the discount factor. We forgot discount factor for a long time, but that's part of the deal too. If you do have a discounted PAM DP, discounted FDP, and you lost your eyes, you still have a discounted PAM DP. The world doesn't say, oh, poor guy lost eyes, let's not do discounting anymore. Right? It's just, it has nothing to do with, the reward model has nothing to do with whether you had sensing or not. Okay, so in this case, I'm just assuming gamma is 1. So you got the reward of being in 0 plus gamma times the expected reward of the next states. 0.9 times R0 plus 0.1 times R1. That is 0.1 if gamma equal to 1. Okay. Similarly, for staying in 1, it's 1.9. Okay. So this gives you this nice picture, right? So 0.1 here and 1.1 here. And so the alpha, the value of stay action, value of the stay policy, as the belief state changes this way, would basically be that line. And similarly, I can compute the go actions value. Okay, and the go actions value would essentially be between 0.9 and 1.1. Again from this. So each value changes in the belief state in that according to that line. Okay. Okay. Now let's actually look at this. So clearly, if you have the choice, okay, first of all, realize the following thing. The value in the middle. So first of all, if you are here, if you're in this belief state, if I tell you you're in this belief state, which would you pick? Clearly, you pick this. Similarly, if I tell you I'm in this belief state, you'll pick this. So clearly, the value of the belief state over the belief state, the value function changes that way, and it has to be remembered as a piecewise linear function. Okay, the value of the belief states is a piecewise linear function. And a couple of things are worth noting. Even though this picture doesn't make it very clear, it turns out this little point is ever so lower compared to the edges. Uncertainty can never be good for you. You see what I'm saying? Uncertainty about the state you are in cannot be good for you. So these piecewise linear functions will always be like that. They will come down in the middle and reach higher values in the edges. That sort of makes sense. Okay? So at this point, I have computed essentially the optimal policy for one step horizon, one horizon. See what I'm saying? Okay. Now the question is, how do I then use this to compute the optimal policy for the two horizon case? Okay. Now the interesting thing is, if I can live for two steps, then notice that I can decide to do an action now. Let's say state first step. Then I need to also tell you what action I will do in the next step. That's what having a plan is all about. If you told me, no, I'll just tell you what action I'm going to do now, and then show me what happens, and I'll decide what action to do next, then you have no plan. Then you're reacting. You see what I'm saying? Okay, so the plan, if you have a plan, it has to be expressible in this form. So I'll do this action state, and then clearly I would either, my evidence will either say I'm in 0th state or I'm in 1st state. If it says I'm in 0th state, I'm really in 0th state with 0.6 probability and probably in 1st state in the 0.4 probability. If it says 1, then I'm in 1st state with 0.6 and 0th state with 0.4. Okay, then I have one more step to go. One more step to go. Okay, so then I throw in one of the one-step actions here. More generally, if I have completed k minus 1 steps of the approach and found out the values of the k minus 1 step plans, and I'm trying to compute the kth horizon, then I will essentially put an action, let's say AI, right? Consider all the possible evidences that can occur, E1 to Ek, and throw in one of the k minus 1 step, one of the k minus 1 step plans, k minus 1 step policies under each of these nodes. That will give me a conditional plan. And you can see how the number of conditional plans is going to exponentially increase as the depth increases. You see what I'm saying? Because if there were tau of k minus 1 conditional plans here, then tau of k, the number of plans of conditional plans at the kth level, depends on the number of conditional plans at the k minus 1 level. How does it depend? In particular, I can do any of the actions, and for each action under each evidence, I can put any of these. Right. So I could put any one of these tau k minus 1 plans here, again here, again here. So tau k minus 1 power the number of evidences. Did you see that? Okay. So this would be tau k minus 1 power z, where z is the number of different evidences, number of different observations you can get. That would be the total number of plans you will get with one action on top. And there are k actions. If there are n actions, then you throw n on top. So if there are actually a actions, you have to throw a here. So a times tau k minus 1 power z. Okay, and then this is a reconciliation, and tau 1 is just the number of actions. Okay. Now, okay, that's sad. I mean, basically, it should be, it's clear that the number of possibilities, number of potential plans you have to consider is going to worsen. Okay. One good thing that you will, and the tricky part, one might actually ask. One of the interesting questions is, here's an interesting question to ask yourself. When we got out of here, could we just have remembered one single conditional plan? Remember, there was two conditional plans, the state plan and the go plan. Could I have just remembered just one of those plans and forgotten the other? In a way, you would think that should be possible, right? Maybe you should just pick the maximum at each level, so only one winner comes up. But what happened is, this guy is the winner over this region, this guy is the winner over this region. You can't throw any of them out. That's the depressing part. Do you see what I'm saying? So intuitively you would think, hey, if I just have to pick one optimal tree at each level, hopefully I don't have to keep around all these bosons. And I don't have to consider putting them under the next level's conditional plans. Because if it's dominant, if it's not ever going to be part of the optimum, why should I care? But the problem is, whether or not it's going to be part of the optimum and one level to go is determined by this piecewise linear approximation. Anybody who is taking part in that upper annular is still in the plane. You can see this either as a bug or a feature. It's a bug if you are hoping that there will be a single winner. It's a feature if I were to tell you that actually there is one other action called boso action, and the boso action would have been here. Okay? So then you compute it. You had to compute the boso actions value at state 1 and state 2 and find the the hyperplane. But you realize that this hyperplane is dominated by the two other hyperplanes everywhere. Like everywhere. So you don't need to ever remember this. Okay? So if you don't remember what you're supposed to remember, you lose soundness. You won't get the optimal value function. If you keep remembering stuff that you don't need to remember, you just become inefficient. Okay? COMDP algorithms would basically be sound as long as they keep all these things around. But they'll be very, very inefficient if they also keep the dominated vectors around, dominated policies around. Because remember, every dominated policy, that means it's a boso policy, will then go and remember that any dominated policy should not ever be put in any of these places. If you are completely dominated in a k-1 level, you should never be part of the kth level optimal policy. Who said this? Bellman. When in doubt, say Bellman. That's the Bellman optimality. If you are dominated like across the board, right, then you should not be part of any one of these evidence, any one of the candidate functions. You see what I'm saying? Okay. So the total number of, k-size policies you have to consider is given by this. But if you were to take time and start considering at the k-1 level, remove all the policies which are fully dominated, and if you are lucky, in the sense your problem has some nice structure, then you could do much less than these number of k-1 guys being added to the kth level conditional plans. To put this in perspective, Russell and Narvik, that book points out that for this silly problem, this is as silly as it can get, right? And for this silly problem, for 8 ply look ahead, that means 8 depth conditional plans, there are only 2 power 255 of them. You've seen the enemy, this is it. Okay, nothing else. NP completeness is for like lame, lazy people. This is the real stuff. And then you go from here to TechCOMDP and you think this is for the lame people. But so there are 2 power 255 distinct 8-sized, 8 depth conditional plans. 8 depth conditional plans. Basically, they're sort of like the number of binary trees. Because this is as binary as you can get. You only have 2 actions, you have only 2 evidences. So the conditional plan is always a binary tree. Okay. However, in fact, he says that there are only about 44 of them are undominated. That means they actually take part somewhere in the envelope of the optimal value function. You guys, what happened? Did they say something wrong?
It's just a really big number.
I know, yeah, okay. But you guys know, for example, that the people from linear programming know that one of the neat things that you care about is slack, the constraints which actually don't affect the optimum. Okay, so in LP basically you also have this sort of an issue. So if you have two-dimensional LP, you have a whole bunch of hyperplanes, right? So there will be a whole bunch of hyperplanes, and you're trying to figure out which of the corners is the optimum. Okay, now it turns out sometimes there may be constraints. One of the hyperplanes may be like that. That means that hyperplane, that constraint is actually not affecting the optimum at all. Okay, and trying to figure that out improves the efficiency. In this particular case too, trying to do the, if you do the part about figuring out which particular lines are dominated, this takes some time, by the way. It's not obvious. You have to spend some time to check the dominated ones and remove it. But it's worth spending that time because every loser you keep will increase your work exponentially as you go up. Okay, so in this particular picture, actually, all they showed was there are actually how many plans of size 2 are there? How many plans of size 2 are there? There will be 8 plans of size 2. Convince yourself for this problem. I mean, 8 policies of size 2. Okay, and it turns out then that, and all of them depend only on, so basically in computing the value of this plan, let's say, this policy, okay, I would use essentially again the Bellman equation, which as part of computing its value would use the value that you computed of the k-1th level policy. Okay, and since in fact, so the k-1th level policy would be what is the value of stay and what is the value of stay in this particular case. That's the only ones I would use in computing the value of this guy. Okay, so using that, I will again get lines. I will get essentially each one of these plans will have a linear value function over the unit state space. But then now there are 8 lines. I need to take the upper envelope. And that upper envelope tells me, in essence, that, so if the upper envelope tells me in essence, so this is my upper envelope, right? In fact, again, this is a sad scenario, right? Because is there a two-size plan that is dominated according to this? Is somebody can be removed, you think? Actually, on top there one. Yeah, sorry. This one, of course, is not. Okay, so this is, if I look at this, I'll feel very sad. You should look at this. Okay, if you look at this, you can see, for example, these dotted lines, they're all dominated. That means you don't need to remember those particular conditional plans of size 2 ever. And when you are computing the conditional plans of size 3, they will never be in the plane. Remember, conditional plans of size 3 will involve putting an action A and putting one of the conditional plans of size 2 at each evidence. The guys who are already losers in the level size, at level 2 will never come to level 3. That's the huge improvement because of the substructure of the optimal. Optimal plan will have optimal subplans. Okay. Now the only tricky thing that you want to understand is that it's not that there's a single plan that you need, a single policy that you get to remember. You have to remember every policy that is the dominating one for however small a region of the unit space. If you are particularly unlucky, every policy might have its own little niche where it will be the optimal one. And in that, in which case optimal policy construction. Again, all computer science people can do is if there is structure to be exploited, exploit it. you can be yelled at if you did not exploit the structure that was available. If you didn't, exploit it by just, if you didn't just randomly approximate the problem and throw away plans that can be part of the optimal policy and said, well, what the final policy I came up with is optimal, that's not right. It took less time, but that's not, So you should decide upfront, are you trying to give approximate or optimal? If you're doing optimal, all you can do is if there is a dominated plan, don't carry it around. It's basically wasting your time. It's just humongously going to increase the number of conditional plans you have to consider. Okay? That's it. Okay? And this is basically the way optimal policies are constructed for k-depth. Okay, and this is the very first algorithm. There are many improvements over the. Okay, this is what I was showing you. But there are many improvements over this value iteration function, which are approximations in their own sense. Okay, notice that just as MDPs had approximations directly on the value iteration, like RTDP, okay, and also like LRTDP. And also approximations on like online, go k-depth and just do the action that you can hit. So I already talked about one type of approximation for MDPs, which is the k-depth approximations. And I never talked about how to approximate the entire value function. Okay, and there are approaches, basically, in fact, one very good approach, if you're into this stuff, is point-based value iteration, which in essence tries to realize that not all belief states are created equal. So it only considers some of the belief states in doing the value iteration. And it will again, only be approximate in terms of the value function. Okay. And the final thing is that one question is, what if this upper envelope is infinitely crinkly? If it's fractal, right? If it's fractal, then in essence, every possible, every point of the belief space has its own separate plan. The thing that is actually saving you is there are contiguous portions of the belief space where the optimal thing to do is the same. You see what I'm saying? Now this is in a two-dimensional case. In a simplex, in a three-dimensional case, there will still be contiguous contiguous regions. What if every point has its own separate policy? And you go epsilon distance from this point, the policy changes, optimal policy changes. Is that possible? Yes, it's possible. And because of which, essentially, computing, in such cases, just representing the value function is out of question. Okay. Although we won't do it in this class, you may want to look at this. Infinite horizon POMDP problems are interesting mathematically because it's not even obvious upfront that actually you can have a tractable policy for it, tractable value function for it. They can be infinitely crinkly. However, for certain classes of problems, there do exist, even for infinite horizon POMDPs. There are results showing that they won't be infinitely crinkly. They would still be expressible as piecewise linear. You may hate it when your piecewise linear approximation has 15,000 hyperplanes, but you will really hate it if it has infinite number of hyperplanes. And all these guys are saying is, in fact, there are, for certain cases, there are in fact, finite number of hyperplanes that will represent the optimal value function exactly. Okay, so we will stop here, and the good news is I will not ask a POMDP question more than depth 5. So you don't need to deal with 2 power 255. No, less than that, maybe 2 power 150. That's it.